What if one of the most trusted ideas in modern physics is wrong, not slightly inaccurate, not in need of adjustment, but fundamentally flawed? Because right now, new observations from the James Webb Space Telescope are forcing scientists to reconsider a theory that has stood unchallenged for over 50 years. A theory created by one of the greatest minds of the 20th century, Stephen Hawking. And the claim is as bold as it is unsettling. Hawking may have been wrong about black holes. This isn't a minor correction or a technical refinement. The new evidence suggests that one of Hawking's most famous predictions, the idea that shaped how we understand black holes, space, and even time itself, might not match reality at all. The very concept that made Hawking a household name now appears to be under serious doubt. But this isn't just a scientific shift. It's also a human story. Hawking, despite living with a devastating illness, made some of the most profound contributions to modern physics. His work inspired generations. It redefined how we think about the universe. So saying he might be wrong doesn't diminish his brilliance, it highlights something deeper. Science evolves by questioning everything, even its most respected figures. To understand what's happening now, we need to go back to what Hawking actually proposed. In 1974, Hawking published a groundbreaking paper titled Black Hole Explosions. In it, he introduced an idea that seemed almost impossible at the time. Black holes, objects known for trapping everything, even light, might not be completely black. They could emit radiation. This was a radical shift in thinking. By definition, nothing escapes a black hole. Its boundary, known as the event horizon, acts like a one-way surface. Matter and energy can fall in, but nothing comes out. Or at least, that's what scientists believed. Hawking showed that when you bring quantum mechanics into the picture, things change. Near the event horizon, the intense gravitational field interacts with the quantum vacuum in a very unusual way. Tiny particle pairs, one particle and one antiparticle, constantly appear and disappear in empty space, but near a black hole, these pairs can be separated. One particle falls into the black hole, the other escapes, and that escaping particle carries energy with it. That energy has to come from somewhere. It comes from the black hole itself. Over time, this causes the black hole to lose mass. Slowly, gradually, it shrinks, and eventually it disappears completely. This process became known as Hawking radiation. It's incredibly weak. For a black hole the size of a star, the temperature of this radiation is barely above absolute zero, almost impossible to detect. But the implications are enormous. First, it means black holes have temperature. Before Hawking, scientists believed they were completely cold. Zero temperature, no radiation. Hawking proved otherwise. And interestingly, the smaller the black hole, the hotter it becomes. Second, it means black holes have entropy. In thermodynamics, temperature and entropy are linked. If something has temperature, it must also have entropy, a measure of disorder or information. And in black holes, this entropy is massive, proportional to the surface area of the event horizon. Third, black holes are not eternal. They don't last forever. As they emit radiation, they lose mass. Given enough time, every black hole should completely evaporate. And finally, this leads to one of the biggest mysteries in physics, the information paradox. If a black hole disappears, what happens to everything that fell into it? Quantum mechanics says information can never be destroyed, but Hawking radiation appears random. It doesn't seem to carry any information about what the black hole consumed. This contradiction has puzzled scientists for decades. Hawking radiation sits at the intersection of two major theories, quantum mechanics and general relativity. It's one of the few predictions that tries to connect both worlds. And for years, it has been considered one of the most important results in theoretical physics. But now, new observations suggest something isn't adding up. To understand why, we need to look at a special type of black hole, primordial black holes. Unlike black holes formed from collapsing stars, primordial black holes are thought to have formed in the early universe, just moments after the Big Bang. Instead of stars, they emerge from tiny fluctuations in density in the hot, dense plasma of the early cosmos. What makes them important is their size. These black holes could be extremely small, even microscopic. And that matters because smaller black holes behave very differently. According to Hawking's theory, the smaller the black hole, the hotter it is, and the faster it evaporates. A black hole with the mass of a star would take longer than the age of the universe to evaporate. But a much smaller one, say, the mass of a mountain, would evaporate much faster. In fact, there's a critical range of mass where these black holes should be reaching the end of their lives right now. And their final moments should be dramatic. As they shrink, they heat up. They release intense bursts of high-energy radiation, gamma rays, particles, and possibly even exotic forms of matter. These final explosions should be detectable. For decades, scientists have searched for these signals. They've scanned the sky for gamma-ray bursts. They've analyzed cosmic rays. They've looked for any sign of evaporating black holes. And they found nothing. This absence was usually interpreted in a simple way. Those black holes probably never existed. But now, the James Webb Space Telescope is forcing scientists to rethink that conclusion. Because instead of finding nothing, it may have found something far more troubling. And that's where the real mystery begins. Because instead of finding nothing, the James Webb Space Telescope may have uncovered a signal that simply shouldn't exist. And that changes everything. To understand why, we need to look closely at what was actually observed. These findings didn't come from a single dramatic image or an obvious explosion in space. They came from something far more subtle and far more powerful: deep field observations, long exposures aimed at the faintest light in the universe. Webb focused on distant regions of the cosmos for extended periods, collecting photons that had traveled for billions of years. The primary goal was to study early galaxies, but hidden within that data was something else entirely: the cosmic infrared background. A faint, diffuse glow that fills the space between visible objects. This background isn't random. It's made up of light from distant galaxies, interstellar dust, and other known sources. Scientists have studied it before, but never with this level of sensitivity and resolution. So when researchers carefully removed all known contributions, every galaxy, every star, every trace of dust, they expected the remaining signal to fade into near nothingness. But it didn't. What remained was a faint excess, a subtle glow that couldn't be explained by any known source. At first, that might not sound like much, but in astrophysics, an unexplained signal is often where the most important discoveries begin. This excess had very specific properties. Its spectrum, the distribution of light across different wavelengths, didn't match stars, galaxies, or any familiar cosmic object. It wasn't thermal in the usual sense. It didn't behave like radiation from hot gas or dust. Instead, it pointed towards something compact, dense, and unusual. Then there was its spatial distribution. The signal wasn't uniform. It showed faint clustering patterns that suggested these sources were linked to the large-scale structure of the universe. That ruled out instrumental errors. It also ruled out random noise. This was real. And then came the intensity. The amount of infrared light detected was consistent with a population of compact objects contributing a small but meaningful fraction of the universe's total mass, possibly even a portion of what we call dark matter. So naturally, scientists began testing explanations. Could it be faint galaxies we haven't detected yet? The spectrum didn't match. Could it be brown dwarfs, failed stars drifting through space? The distribution didn't fit. Exotic particles? No known particle could produce this kind of signature. One by one, the usual suspects were ruled out, and what remained was something unexpected. The best explanation that matched all the data was a population of primordial black holes. Not large ones, not the kind formed by dying stars, but small, ancient black holes formed in the earliest moments of the universe. And here's where the problem begins. According to the theory developed by Stephen Hawking, black holes of a certain size should not exist today. They should have evaporated billions of years ago through Hawking radiation. But the signal detected by Webb suggests that these objects are still here. They haven't evaporated. They haven't exploded. They're still present, quietly influencing the universe. To understand why that's such a big deal, we need to talk about the numbers. Hawking's theory gives very precise predictions. The temperature of a black hole is inversely proportional to its mass. That means the smaller the black hole, the hotter it becomes. And the hotter it is, the faster it radiates energy. This leads to another key relationship, the evaporation time. The lifetime of a black hole scales with the cube of its mass. Larger black holes last longer. Smaller ones disappear quickly. A black hole with the mass of a star would take far longer than the current age of the universe to evaporate. But a much smaller black hole, one with the mass of a mountain, would evaporate in roughly the same time as the universe has existed. Even smaller ones should already be gone. Completely gone. But the data from Webb doesn't just suggest black holes in the safe mass range, the ones that should still exist. It also hints at a broader distribution, one that extends into the range where evaporation should have already happened. That creates a contradiction. Either the mass distribution is somehow limited in a very precise way, which doesn't match the shape of the signal, or Hawking's prediction about evaporation is incomplete. Researchers examine both possibilities carefully, and the data lean toward a more uncomfortable conclusion. Evaporation has not occurred the way we expected. These primordial black holes are still there. And if that's true, then something fundamental in our understanding of black holes is wrong. So what could explain this? One possibility is that the assumptions behind Hawking's calculation don't hold in extreme conditions. His work relied on quantum field theory applied to curved spacetime, a powerful approach, but one that includes approximations. For example, the behavior of the quantum vacuum near the event horizon is assumed to follow standard rules, but the environment around a black hole is anything but standard. It's the most extreme region in the universe. If the vacuum behaves differently there, the entire mechanism behind Hawking radiation could change. Another key assumption involves the nature of the event horizon itself. Hawking treated it as a smooth, well-defined boundary. But in reality, quantum effects might make it far more complex, fluctuating, unstable, or even fundamentally different from the classical picture. If the horizon isn't what we think it is, then the process that produces radiation might not work the way we expect. There's also a deeper issue known as the Transplanckian problem. The particles involved in Hawking radiation originate from modes that, when traced back in time, reach incredibly small wavelengths far smaller than the Planck scale, where our current understanding of physics breaks down. At that scale, we simply don't know how nature behaves. Hawking's calculation assumes that known physics still applies there. But if it doesn't, the predicted radiation might never emerge at all. Some theories suggest that modifications at these tiny scales could suppress or even eliminate Hawking radiation entirely. And if that's the case, then the black holes we expected to vanish might persist indefinitely. There's also the question of feedback, what physicists call back reaction. Hawking's original calculation treats the black hole as a fixed background, ignoring how the radiation itself changes the system. But as a black hole loses mass, its temperature increases, which should affect how it radiates. This creates a complex, time-dependent process. When researchers include these effects, the outcome becomes less clear. Some models suggest that evaporation slows down. Others suggest it might stop entirely, leaving behind a stable remnant. And those remnants could still exist today. All of these possibilities point to the same conclusion. The theory might not be wrong in principle, but it could be incomplete. And that brings us to an even deeper question. What if the problem isn't just with black holes, but with our entire approach to combining quantum mechanics and gravity? Because Hawking radiation sits right at that intersection. If it fails, then the bridge between those two worlds might need to be rebuilt. But before we go that far, we have to ask a more basic question. What if the interpretation itself is wrong? What if the signal Webb detected isn't coming from black holes at all? Because in science, especially at this level, caution isn't optional, it's essential. And in the next part, we're going to examine that possibility in detail. Because before rewriting the laws of physics, we need to be absolutely sure we're not misreading the evidence. Because before we start rewriting the laws of physics, we have to confront a simpler possibility. What if this signal has nothing to do with black holes at all? That question might sound conservative, but in science, it's necessary. Extraordinary claims demand not just strong evidence, but the elimination of every reasonable alternative. And right now, that process is still unfolding. The excess infrared signal detected by the James Webb Space Telescope is real. That much is not in doubt. The challenge lies in understanding its origin. One possibility is that the signal comes from extremely faint galaxies, objects too dim or too distant to be individually resolved. The early universe likely contained countless small galaxies that have since faded or merged into larger structures. Could their combined light create this unexplained glow? At first glance, that seems plausible. But when researchers modeled this scenario, the results didn't match the data. The spectrum, the way the light spreads across wavelengths, didn't align with what we expect from stars or galaxies. Even the faintest galaxies still follow predictable patterns. And this signal doesn't. Another idea involves interstellar dust. Dust grains can absorb ultraviolet light and re-emit it in the infrared, creating a diffuse background glow. This process is well understood and has been observed in many regions of space. But again, the details don't fit. The spectral signature of dust emission is distinct, and the Webb data shows something different. The distribution of the signal also doesn't match how dust would behave on cosmic scales. Dust tends to cluster in certain environments, not spread in the subtle, structured way this signal does. Then there are brown dwarfs, objects too large to be planets but too small to sustain nuclear fusion like stars. These failed stars emit primarily in the infrared and could, in theory, contribute to the background. But brown dwarfs are not distributed in a way that would produce the observed clustering pattern. They follow stellar populations, and their contribution has already been accounted for in existing models. What about something more exotic? There are theoretical particles, dark matter candidates that could decay or interact in ways that produce infrared light. Some models predict weak signals that might resemble what Webb has seen. But here's the problem. No known particle behaves this way. The spectrum, the intensity, and the spatial structure all impose strict constraints. Any proposed particle would need to match all three, and so far, none do. One by one, the alternatives fall short. And that's why primordial black holes remain the leading explanation. Not because they're the simplest idea, but because they're the only one that currently fits all the evidence. Still, even this interpretation raises difficult questions. If these objects are indeed primordial black holes, then their properties must align with the signal. That includes their mass, their distribution, and their behavior over time. And this is where the tension with Hawking's theory becomes unavoidable. According to the equations developed by Stephen Hawking, black holes below a certain mass should have completely evaporated by now. Not partially, not slowly, completely. Gone. But the signal suggests otherwise. It implies a population of compact objects that still exist in a mass range where they shouldn't. And not just a few isolated cases, but a distribution wide enough to produce a measurable cosmic signal. So either something is preventing their evaporation, or our understanding of that process is incomplete. This brings us back to the theoretical side of the problem. One idea that has gained attention is the possibility of black hole remnants. Instead of evaporating entirely, a black hole might shrink down to a minimum size, a stable endpoint where evaporation stops. This concept appears in several approaches to quantum gravity. The idea is that once a black hole reaches a certain scale, often near the Planck mass, it can no longer lose energy through standard mechanisms. It becomes stable. If such remnants exist, they could accumulate over cosmic time. And if primordial black holes formed in large numbers early in the universe, many of them could still be present today in this remnant state. That would explain their persistence. But it also raises new questions. What are these remnants made of? How do they store information? And why haven't we detected them more directly? Another possibility is that black holes don't evaporate in isolation. Instead, they might interact with their environment in ways that balance the energy loss. For example, they could absorb energy from the quantum vacuum or surrounding matter at a rate that offsets their radiation. In that case, evaporation wouldn't stop, but it would slow down dramatically. Enough to allow these objects to survive until today. There's also the idea that Hawking radiation itself might be modified, not eliminated, but altered. The particles emitted might carry different energy distributions, or the process might be less efficient than originally calculated. If that's true, then the predicted lifetimes of black holes would change, and suddenly, the presence of these objects wouldn't be so surprising. But all of these explanations share one thing in common. They require us to go beyond the original theory. And that's where the real challenge begins. Because Hawking's prediction isn't just a standalone idea. It's deeply connected to our broader understanding of physics. It ties together thermodynamics, quantum theory, and general relativity. Changing it isn't a small adjustment. It's a structural shift. And that brings us to an even deeper layer of the problem. Because if black holes don't behave the way we thought, then what does that mean for the information they contain? Because at the heart of this entire discussion lies a question that has troubled physicists for decades. What happens to information inside a black hole? According to quantum mechanics, information can never be destroyed. Every particle, every interaction, every detail about a system must, in principle, be preserved. But black holes seem to challenge that rule. When something falls into a black hole, it disappears behind the event horizon. From the outside, it's gone. And if the black hole eventually evaporates as predicted by Stephen Hawking, then everything it contains seems to vanish with it. The radiation that escapes doesn't appear to carry any information about what fell in. It looks random, thermal, featureless. This creates a contradiction. If the information is lost, quantum mechanics is violated. But if it's preserved, then our understanding of black holes must be incomplete. This is known as the black hole information paradox. And for years, Hawking himself argued that information really is lost, that black holes erase it completely. But most physicists resisted this conclusion. The laws of quantum mechanics have been tested repeatedly, and they've held up every time. So instead of abandoning quantum theory, researchers began looking for ways to resolve the paradox. Some proposed that the information escapes gradually, encoded in subtle correlations within the radiation. Others suggested that it's released at the very end of the evaporation process, in a final burst. There are even ideas that information is stored on the surface of the black hole itself, a concept known as the holographic principle. But all of these solutions depend on one key assumption, that Hawking radiation exists and behaves in a specific way. If that assumption fails, the entire framework changes. And this is where the new observations become so important. Because if primordial black holes haven't evaporated, then maybe the paradox doesn't arise in the way we thought. Maybe the reason we can't find the information is because it was never lost to begin with. It's still there, inside black holes that never fully disappeared. This leads to a more radical idea. What if the conservation of information actually prevents black holes from evaporating completely? In other words, what if the laws of quantum mechanics don't just allow black holes to exist but actively stop them from vanishing? If there's no consistent way to encode information into radiation, then evaporation might be incomplete by necessity. The black hole would be forced to persist, and that persistence could explain exactly what the James Webb Space Telescope is seeing. A hidden population of ancient black holes still present in the universe, quietly carrying the information of everything they've ever absorbed. If this idea is correct, it would resolve the paradox in a completely different way. Not by changing quantum mechanics, not by modifying the radiation, but by changing the fate of black holes themselves. Of course, this is just one possibility. There are others that go even deeper into the unknown. Because ultimately, all of these questions point to a larger issue, our incomplete understanding of quantum gravity. Hawking radiation is a semi-classical result. It combines quantum fields with a classical description of spacetime. But that's not the full picture. A true theory of quantum gravity would treat spacetime itself as a quantum object. It would describe how gravity behaves at the smallest scales, where the known laws of physics begin to break down. And different approaches to quantum gravity make different predictions. Some versions of string theory suggest modifications to black hole behavior. Loop quantum gravity introduces discrete structures in spacetime that could affect how horizons form and evolve. Other models propose entirely new phenomena, states of matter or energy, that only appear under extreme conditions. The problem is, we don't yet know which, if any, of these theories is correct. And that's why observational evidence is so valuable, because it gives us something solid to test. If the data from Webb continues to support the existence of primordial black holes in this critical mass range, then many current theories will be ruled out, and others will gain support. In that sense, these observations aren't just about black holes. They're about the fundamental nature of reality. They're about how space, time, and information are connected at the deepest level. But before we jump to conclusions, there's one more possibility we need to consider. What if the signal is real, but our interpretation of it is not? Because even the most precise instruments can only show us what's out there. Understanding it correctly, that's a different challenge entirely. And in the next part, we're going to explore just how easy it is to get that wrong, and what it would mean if we have. Because even when the data is real, and the signal is undeniable, interpretation can still lead us in the wrong direction. And that's exactly where we are now. The observations from the James Webb Space Telescope are precise, carefully analyzed, and incredibly sensitive. The excess infrared signal exists, the clustering pattern exists, the spectrum doesn't match known sources. But turning that signal into a conclusion, that's where uncertainty begins. So before we accept that primordial black holes are hiding across the universe, and before we question the work of Stephen Hawking, we need to take a step back and examine the limits of what we actually know. The first issue is modeling. When scientists subtract known sources from observational data, they rely on models' mathematical representations of galaxies, dust, stars, and other contributors. These models are incredibly advanced, but they are not perfect. If even a small component is underestimated or misunderstood, it can leave behind a residual signal that looks like something new. For example, extremely faint galaxies at high redshift galaxies, so distant that their light has been stretched deep into the infrared, could still be contributing to the background. If their population is larger or more complex than expected, they might create exactly this kind of excess. And because these galaxies are too faint to resolve individually, they would appear as a diffuse glow. There's also the question of cosmic dust, not the dust we see in nearby galaxies, but ancient dust from the early universe. Its properties might differ from what we observe locally. Different grain sizes, different compositions, different emission patterns. If that's the case, our current models might not fully capture its behavior. And again, that could produce a signal that appears unfamiliar. Another possibility involves instrumental effects. Even though the James Webb Space Telescope is one of the most advanced observatories ever built, no instrument is completely free from noise or subtle biases. Calibration errors, detector sensitivities, background subtraction methods, all of these can introduce small distortions. Now, scientists are extremely careful about this. The data is cross-checked, reanalyzed, and compared with independent observations. But when dealing with signals this faint, even minor uncertainties can matter. Then there's the issue of interpretation itself. The moment we see a signal that doesn't match known sources, the natural instinct is to look for new physics. But sometimes, the explanation isn't entirely new, it's just incomplete understanding of something familiar. In this case, the signal has been interpreted as emission from matter accreting onto compact objects, specifically primordial black holes. As material falls toward these objects, it heats up and emits radiation, including infrared light. This process fits the data well, but it's not unique. Other compact objects, under the right conditions, could produce similar signatures, dense star clusters, exotic remnants, or even unknown stages of stellar evolution might mimic the same effect. The challenge is distinguishing between these possibilities with limited information. And right now, the data doesn't give a definitive answer. It gives a strong candidate, but not certainty. There's also a broader concern about statistical significance. In astrophysics, detecting a signal is only the first step. The next step is determining how confident we are that it's real and not the result of random fluctuations or systematic errors. This involves repeated observations, independent verification, and consistency across different datasets. As of now, the Webb observations are compelling, but they are still being studied. Other teams are analyzing similar regions of the sky using different methods, trying to confirm or challenge the findings. And until that process is complete, the interpretation remains provisional. That doesn't make it weak. It makes it responsible, because science doesn't move forward by jumping to conclusions. It moves forward by testing them again and again until only the most consistent explanation remains. So where does that leave us? We have a signal that doesn't match known sources. We have a leading explanation, primordial black holes, that fits the data but challenges established theory. And we have alternative possibilities that haven't been completely ruled out. This is exactly the kind of situation where science becomes most interesting. Not because we have answers, but because we don't. Because this is the moment where ideas are tested, assumptions are questioned, and new frameworks begin to take shape. If the interpretation is correct, then Hawking's prediction about black hole evaporation needs to be revised. Not discarded entirely, but reconsidered, expanded, or corrected. If the interpretation is wrong, then we've discovered a new gap in our understanding of the universe, one that still needs to be explained. Either way, something important is happening. And the next step is crucial, because what comes next isn't just about analyzing data. It's about deciding what kind of universe we believe we're living in. A universe where black holes slowly disappear over time, or one where they endure, quietly shaping the cosmos in ways we're only beginning to detect. And in the final part, we're going to bring all of this together. Because the answer to this mystery doesn't just affect black holes. It could redefine our understanding of reality itself. So now we arrive at the point where everything comes together. Not with a final answer, but with a clearer view of the stakes. Because what started as a faint signal in the data from the James Webb Space Telescope has grown into something much larger. A challenge not just to a single idea, but to an entire framework that has shaped modern physics for decades. At the center of it all is a simple but uncomfortable possibility, that one of the most celebrated predictions by Stephen Hawking may not fully describe reality. But this isn't a story about being right or wrong. It's about how science actually works. Hawking's theory of black hole radiation was never meant to be the final word. It was a breakthrough, a bridge between two worlds that had never been fully connected before: quantum mechanics and gravity. The smallest scales of nature and the largest structures in the universe. For years, that bridge held. It guided research. It inspired new theories. It helped physicists explore questions that once seemed impossible to approach. And now, it's being tested. Not in a laboratory, not through equations alone, but through direct observation of the universe itself. That's what makes this moment so significant. Because when theory meets observation, something has to give. Either the observations are incomplete, and we refine our measurements until they align with existing theory, or the theory itself needs to evolve. And right now, both possibilities are still on the table. If future observations confirm the presence of primordial black holes in the mass range suggested by Webb, then we'll need to rethink how black holes behave over time. We may discover that evaporation is slower than predicted, or that it stops at a certain point, or that entirely new processes are involved. Each of these possibilities opens the door to new physics, new ways of understanding space, time, and energy. On the other hand, if further analysis reveals that the signal comes from something else, something we haven't properly accounted for yet, then we still gain something valuable: a deeper understanding of the universe's hidden components, a more accurate picture of how light, matter, and structure interact across cosmic scales. Either way, the outcome is progress. But there's another layer to this story, one that goes beyond equations and observations. It's about how we think. Because it's easy to assume that scientific knowledge moves in a straight line, that once an idea is accepted, it stays fixed, that discoveries simply add to what we already know. But that's not how it works. Science is not a collection of permanent truths. It's a process, a constant refinement of ideas based on new evidence. And sometimes, that process leads us back to the very foundations to questions we thought were already answered. That's where we are now, revisiting the nature of black holes, re-examining the relationship between quantum mechanics and gravity, rethinking the fate of information in the universe. These are not small adjustments. They are fundamental questions. And the fact that we're still asking them, still testing them, means we're doing something right. Because progress doesn't come from certainty. It comes from doubt, from the willingness to question even the most respected ideas, even those proposed by someone like Stephen Hawking. And that's not a weakness of science. It's its greatest strength. Because every time a theory is challenged, we get closer to the truth. Not by defending what we already believe, but by being open to what the universe is actually telling us. So where does this leave us? With a signal that doesn't fully fit, with a theory that might need revision, and with a universe that continues to surprise us. Maybe black holes don't evaporate the way we thought. Maybe they leave behind remnants. Maybe they're more stable, more persistent, more influential than we ever imagined. Or maybe we're still missing a piece of the puzzle. Something subtle, something hidden. Something that connects all of this in a way we haven't yet seen. That's the nature of discovery. It doesn't arrive fully formed. It begins with questions. And right now, those questions are pointing us towards something deeper. Something that could reshape our understanding of reality itself. So the next time you hear that a theory has been proven wrong, remember this. It doesn't mean science has failed. It means science is working exactly as it should. And somewhere in the data we're still analyzing and the ideas we're still testing, the next breakthrough is already waiting.